Alright, so in this video I'm going to be looking through some revision on the optics topic. So I'm going to be looking at reflection, refraction, total internal reflection, and then finally diffraction. So those are kind of the four areas that it's going to focus on. So we're going to start off with reflection, and we're going to draw a wavefront diagram to show reflection. So a diagram should look something like this. So we should see equally spaced wavefronts going in to the barrier and then equally spaced wavefronts coming out. And one of the things I'm looking for here is that the distance between the wavefronts, the wavelength, should be the same before and after reflection. And then the other rule that we should be obeying is that the angle of incidence should be equal to the angle of reflection. And we look at that from the rays that you can see in the center of the wavefronts there. The angle to the normal should be the same for both of them. Okay, so that's reflection. So it says, should the distance in the wavefronts change before and after reflection? Explain your answer. So I just said that no, it shouldn't change, we should have it the same, but the question is why? So the first thing I think about is, well, the medium is the same before and after. We're in air. So the wave speed is going to be the same before and after. So no change in speed. The frequency is also going to be the same before and after, because the only thing that can change frequency is the actual source emitting it. So that's the same. And if those two are the same, that must mean the wavelength is the same using the wave equation, V equals lambda f. So is the image formed in the mirror real or virtual? It is going to be virtual because no light rays actually pass through where the image is.
Okay, so moving now on to refraction. So we've got light travelling from a less dense to a more dense medium, bends towards the normal, and light travelling from more to a less dense bends away from the normal. And those things you just have to remember. And the way I remember this is by writing the letters in alphabetical order. So if you go from left to right, if you go from less to more, we can see we're going towards N, towards the normal. Or if you see we go from M to L, you can see we're going away from the normal. So that's how I actually remember which way round that works. Okay, so then to model refraction, we use Snell's law. I usually write it in this form. You see it in a variety of different forms, but this to me is the most helpful way of writing it. And again, you just have to remember the equation and the terms in it. So N1, the refractive index before the boundary, I is the angle of incidence measured to the normal, N2 is the angle of refraction, is the refractive index after the boundary, and then R is the angle of refraction. Okay, so next we want to sketch a wavefront diagram of a light wave travelling from air into glass. So here is my diagram. So this is the one process where we are going to see the wavelength changing. In reflection, diffraction, the rest of it, the wavelength hasn't been changing. So here we can see when it goes from air into the glass, we've shortened the wavelength, and we're going to look at why that is in a second. But the key here is you only see the wavefront change direction when it actually hits the boundary. So you can see the bend point is always along the boundary there. Okay, so why does the wavelength decrease? Well, light travels slower in the more dense glass, okay, so its speed is decreased. But we know from what we've seen before, the frequency isn't changing, because again, we've still got the same source of waves somewhere far away, so the frequency stays the same. Going across a boundary does not change the frequency. So essentially, you can see that if the frequency is constant, if you decrease the speed, you must decrease the wavelength as well to keep that equation consistent. And that's essentially what's happening here. And you can see the shorter wavelength once it's switched into glass. So let's actually put that to use. So we've got a light ray travelling in air, strikes the boundary of the glass where it travels at a speed of 2 × 10⁸ meters per second. Calculate the refractive index. So refractive index is the speed of light in a vacuum divided by the speed of light in a medium. Speed of light in a vacuum or in air is 3 × 10⁸. So we're going to divide that by 2 × 10⁸, which is why I've just cancelled out the times 10⁸. We don't need those. And we can see it clearly comes out as 1.5. And then calculate the angle of refraction in glass using your answer to A, and if the angle of incidence is 30 degrees. So to do this, we're going to use Snell's law. We want to calculate the angle of refraction, so I'm going to make sine r the subject by dividing both sides by n2. Then I substitute in the numbers. The refractive index of air is 1, you just have to remember that. We've just got the refractive index of glass is 1.5, and we've got the angle of incidence is 30 degrees. So we put those numbers in, and that calculates sine r. We take the inverse sine of that, and that gives us the angle of refraction is 19 degrees. So you can see it has in fact bent towards the normal, because the angle is smaller than the angle of incidence. So that makes sense. Okay, so moving on to some total internal reflection. So the critical angle is the angle of incidence when the angle of refraction is equal to 90 degrees. So when it goes along the boundary at 90 degrees to the normal. Total internal reflection can only occur when the wave travels from a more dense medium to a less dense medium. It doesn't work the other way around. So what we're going to do is determine the critical angle for light traveling from glass into air. So again, we're going to use Snell's law. This time we want to find the angle of incidence, because the critical angle is the angle of incidence when the angle of refraction is 90 degrees. N2 is going to be 1 because it's going from glass into air. N1 is 1.5, we calculated that earlier. And then as I said, the angle of refraction is 90 degrees at the critical angle. So we've calculated what sine I is, so we can then calculate what the angle of incidence is, which is the critical angle 42 degrees. So what this tells us is that if the angle of incidence is greater than 42 degrees, we're going to get total internal reflection occurring. So finally, looking at diffraction, you want to sketch a wavefront diagram for a water wave encountering a gap in a barrier the same size as its wavelength. So what we should have is something that looks like this. So on the left we've got the incident waves, and on the right hand side we've got the diffracted waves, and if the gap is the same size as the wavelength, we should get perfect semicircles here. And one thing I would be looking for here is the wavelength should stay the same, because we're still in water on both sides, so we shouldn't have any change in wavelength, because neither the speed or frequency have changed. If we make the barrier wider, so it's much larger, we should get a diagram that looks like this. And again, what I'm looking for here is the center of the waves should be unaffected. So part of the wavefront that goes right through the middle of the gap shouldn't experience any diffraction at all. It's only at the edges that we should be seeing diffraction occurring, which is what you see in the diagram. And again, the diagram doesn't show that awfully well, but the wavelength should stay the same because again, we're in the same medium, water in this case, before and after, and we've got the same frequency, so the wavelength has to stay the same. It looks a little bit like it increases on that diagram, but it doesn't. Okay, so that concludes this video looking at optics and the processes that can occur to light.